A polished answer card slides out of a language model. It has the shape of useful work. It has no test result attached to it, no source, no score, no lineage, no reviewer state. Good looking is not the same as improved. It is not the same as correct. It is not even the same as useful. It just means the model produced something that fits the shape of an answer. That distinction is easy to miss because fluency imitates completion. A program can compile in the imagination of the reader. A legal memo can sound like it has found the right case. A contract clause can sound balanced. A scheduler heuristic can look mathematically tidy. But none of those surfaces tells you whether the work survived contact with the thing it is supposed to answer to. For code, that thing might be a test suite, a runtime measurement, a compiler, a simulator, or a formal property. For legal work, it might be a source span, a controlling jurisdiction, a partner instruction, a redline boundary, a privilege constraint, or a client posture. The common failure is the same. The first output arrives before the workflow has attached the proof of why anyone should rely on it. AlphaEvolve starts from a harsher assumption. A candidate is worthless until it survives a test. That one change moves the system out of one-shot output and into evaluated search. The model is no longer being asked to be the final authority. It is being used to generate mutations. Those mutations are executed. They are scored. The weak ones are pruned. The useful ones enter memory. The next generation starts from what survived. Not AI is evolving in some vague biological sense. Not agents are getting smarter, in the way every demo page says agents are getting smarter. The actual mechanism is more precise. A human defines a world where the candidate can be tested. The model proposes a change inside that world. The evaluator filters survival. The database remembers the candidates worth reusing. Then the loop runs again. If you miss that structure, AlphaEvolve looks like another impressive DeepMind result. If you see it clearly, it is a blueprint for a different kind of AI system. Most AI tools still behave like a person taking a single shot. You ask for code, a memo, a draft, a research answer, a spreadsheet model. The model gives you something. Maybe it is good. Maybe it is wrong in a subtle way. Maybe it is half right and half confident nonsense. The burden moves to you. You have to inspect it. You have to decide what survived. You have to remember what was useful. You have to carry the caveats into the next request. The system produced an output, but it did not create a reliable improvement loop. Tool calls do not solve this by themselves. A tool can fetch, run, search, or edit. The harder question is whether the system has a way to make its own attempts accumulate. Imagine two workflows. In the first, a model writes a candidate program. It looks plausible. You ask it to improve the program. It writes another plausible version. You ask again. It writes a third. Each attempt may contain some good idea, but the workflow itself does not know which idea mattered. It does not know which line improved the score. It does not know which branch should be abandoned. It does not know what to preserve except whatever happens to remain in the prompt. That is not evolution. That is repeated sampling with a memory problem. In the second workflow, every candidate is executed. The score is recorded. Strong candidates can become parents. Weak candidates are pruned instead of being mistaken for progress. Diverse candidates are preserved because the system may need a different family of ideas later. The next prompt is not just try again. It is built from ancestry. Now the system has pressure. A bad candidate does not win because it sounds good. A good candidate does not vanish because the next prompt got crowded. Improvement becomes something the system can carry forward. This is the first thing to understand about AlphaEvolve. It does not make the language model reliable by declaration. It changes the job the model is doing. The model is not the judge. The model is a mutator. It proposes changes. The loop decides what survives. That is why the official paper keeps coming back to automatic evaluation. AlphaEvolve is designed for tasks where a candidate can be assessed by code. A user supplies an evaluation function. The function returns scores. The system can run candidate after candidate against that scoring setup. If the candidate improves the score, it has earned the right to influence the next generation. If it fails, it gets pruned from the survival path. This is also the first boundary. AlphaEvolve is not a universal recipe for every kind of knowledge work. It works best where the world can be made machine-gradable. A scheduler heuristic can be simulated. A kernel can be timed. A generated construction can be checked against a mathematical property. A code rewrite can be run against randomized inputs. Those are not soft judgments. They are survival tests. The reason this matters for legal AI is almost the opposite. Legal work usually does not have a single clean scalar score. A motion is not correct because one function returns 0, 91. A contract redline is not safe because it passed a benchmark. A research memo can be directionally right and still miss the controlling exception. So the lesson is not that law should copy AlphaEvolve literally. The lesson is that serious AI work cannot stop at fluent output. In a legal matter, a claim should not enter the answer just because the model produced a polished paragraph. The claim needs a source span. It needs a citation. It needs a confidence state. It needs a caveat if the authority is limited. It needs reviewer status if a lawyer has accepted, rejected, or modified it. This is where the first iris operation belongs. Citation verification as a gate, not as a decoration after the fact. The answer should not move from retrieved to usable in one jump. It should move through visible states: retrieved, checked, blocked, accepted with caveat, reviewer approved. Those states matter because a legal team does not only need an answer. It needs to know whether the answer is still raw material, whether the citation was actually verified, whether the authority is limited, and whether a reviewer has adopted the conclusion for the matter. Iris is not useful here because it can say AI next to a legal workflow. It is useful if the work product has state. A claim card should carry its source. A caveat should not disappear during handoff. A reviewer should be able to trace the answer backward. The matter should remember what survived inspection. That is the legal version of the same pressure AlphaEvolve makes visible. Fluency is not enough. Survival matters, but survival has to mean something appropriate to the domain. For AlphaEvolve, survival can be a score from executable code. For legal work, survival is more often source-backed, reviewable, governed, and reusable. The common lesson is architectural. Do not trust the first plausible output. Build a system where attempts can be checked, state can persist, and the next step starts from what the workflow actually learned. That is the first pressure point for the whole video. Everything else follows from it. The easiest mistake is to confuse iteration with evolution. They are not the same. A person can ask a model to try again 10 times. That produces 10 attempts. It does not automatically produce cumulative search. The difference is lineage. Lineage means the system knows where an idea came from, what changed, what score it received, and whether it should influence the next attempt. Without lineage, every attempt is just another sample from the model. You can see the failure if you watch a long chat session after the first few turns. The model proposes one answer. You object. It proposes another answer. You correct a detail. It incorporates the correction but may drop something else. You ask for a synthesis. Now the output sounds cleaner, but the working history has become less usable. The system may know that words appeared earlier in the conversation. It does not necessarily know which earlier position was rejected, which was accepted, which was useful but incomplete, and which failed because the evaluator or reviewer found a specific defect. That is why retries can create the feeling of progress while destroying the structure of progress. They produce motion. They do not produce ancestry. This is why just make the prompt longer is such a weak answer. Longer context can hold more material, but it does not decide what should survive. It does not turn a failed attempt into a warning sign. It does not turn a successful substructure into a reusable parent. It does not protect a rare but valuable idea from being buried under cleaner prose. If the system has no structured memory, the next attempt depends on whatever the prompt happens to carry. That is fragile. AlphaEvolve handles this differently. The program database stores candidate programs with their evaluation results. It can sample a parent program. It can sample inspirations. The prompt sampler can build a new prompt using prior programs, scores, feedback, instructions, and context. A child program is not born from a blank chat window. It is born from selected ancestry. The official design is important because the memory is not just a log of previous text. It is scored work. The database stores programs together with evaluation results and outputs. That means a later generation can be influenced by a candidate because it performed well, because it had an interesting structure, because it sat in a useful niche, or because it provides context for a new mutation. A plain transcript cannot do that job by itself. It can show what was said. It cannot decide which prior object should become apparent. That is why the database is not a filing cabinet. It is part of the search algorithm. If you store only the current best program, the search can collapse too early. A single winner may be locally good and globally limiting. You may need a different lineage later. You may need a candidate that was not best overall, but had a structural idea that becomes useful after a different mutation. Evolutionary systems have known this for a long time. The official paper points to ideas from MAP elites and island-based models. The core intuition is simple: preserve useful diversity. Do not let one clean answer erase all the other paths before you know which landscape you are actually climbing. This is where one-shot agents are weakest. They overwrite, they summarize, they compress. They make the working state easier to read but often less faithful to the search. In code optimization, that can mean losing a strange candidate that would have led to a better algorithm. In legal work, it can mean losing the caveat that controls the answer. A matter often contains several live theories. One authority supports the client. Another limits that authority. A footnote creates risk. A partner instruction narrows the drafting posture. A prior redline explains why one phrase cannot be changed. A reviewer has already rejected one path. Now imagine a document comparison workflow. Version 1 has a clause the associate wants to simplify. Version 2 removes a defined term because the model thinks the sentence reads better. Version 3 restores the defined term but changes the indemnity trigger. Version 4 preserves the trigger, but loses the jurisdiction-specific carve-out that made the language safe. If the system only keeps the latest polished draft, the matter has lost the reason each branch existed. The accepted branch and the rejected branch both matter. The rejected branch tells the next reviewer what not to repeat. The accepted branch tells the system which constraints survived. The comparison is not just visual diffing. It is memory of authority. If all of that becomes a smooth summary, the next worker inherits prose, not state. The prose may sound clean because the conflict has been removed. That is exactly the danger. In Iris, the point of matter memory is not to make the prompt longer. It is to keep the important objects separate. The claim stays a claim. The source stays attached. The caveat remains visible. The reviewer note keeps its status. The draft branch does not erase the rejected branch. The next question starts from inspected matter state, not from a compressed story about the matter. That is a different kind of document comparison. Then show me what changed. The system needs to show what changed, why it changed, who accepted it, what source or instruction controlled the decision, and which rejected branch should remain available if the issue returns. In that workflow, a rejected clause is not trash. It is a boundary marker. It prevents the next pass from rediscovering the same bad idea in smoother language. That is the legal analog of lineage. Not because legal work evolves like code, because complex work needs memory that preserves what mattered. AlphaEvolve shows the engineering version of this rule. A candidate without a score is just a suggestion. A score without a database is just a historical fact. A database without resurfacing is just storage. The loop becomes powerful only when memory changes the next generation. That is the bar for any serious AI workflow. The system has to remember in a way that changes what happens next. Otherwise, it is not learning at the workflow level. It is just producing another answer. Lineage is what turns repeated attempts into reusable work. Without it, a system can look busy while the matter stands still. It can generate effort without preserving progress. That is the failure mode this arc is naming. It is quiet, expensive, and easy to miss. It compounds across the matter. AlphaEvolve is not a model. It is not a single agent prompt. It is not a chatbot with tools attached. It is a loop around code. The user begins by defining the task. That means the user provides an initial program, marks the parts of the program that AlphaEvolve is allowed to change, supplies optional background knowledge, and most importantly, defines evaluation code. That setup step is not administrative. It is the control surface. The initial program gives the search a starting structure. It may be simple. It may be expert-written. It may contain a baseline algorithm, a loss function, a heuristic, an optimizer, or a scaffold around the piece that should change. The marked evolution regions define the authority boundary. AlphaEvolve is not simply handed a repository and told to do whatever it wants. The user can mark where evolution is allowed and where the surrounding code should remain stable. In some applications, the model proposes small diffs. In others, the system can permit larger rewrites. That choice changes the risk surface. Optional background knowledge gives the model context that should shape proposals. Problem instructions, design constraints, relevant documents, prior feedback, or hints about what kind of solution is desired. Then the evaluator defines consequence. That last piece is the center of the system. AlphaEvolve is not free to decide what better means. A human defines the evaluatable world. The system searches inside it. The official loop is simple enough to draw in one line. Sample a parent program from the database. Sample inspirations from earlier candidates. Build a prompt from the parent, the inspirations, the scores, the feedback, and the task instructions. Ask the LLM ensemble for a code change. Apply the diff to create a child program. Run the evaluator. Store the child program, its score, and its outputs back in the database. Then repeat. This loop is easy to describe and hard to discipline. Each step has to preserve the boundary from the setup. The prompt cannot forget what region is editable. The model cannot be treated as the evaluator. The child program cannot be accepted because the diff looks reasonable. The evaluation output cannot be thrown away after producing one leaderboard number. The database cannot become a dead archive. The loop works because the artifacts move forward. Parent, inspiration, prompt, diff, child, execution result, score, output, database entry. If any one of those becomes only prose, the search starts losing its machinery. There is another constraint hidden in that list. The model is not editing an abstract idea. It is editing an artifact. That matters because artifacts have boundaries. A diff can be applied or rejected. A full rewrite can be allowed or forbidden. A marked block can be changed, while the surrounding scaffold remains stable. Evaluation can run on the resulting child because the child is still a program, not just a suggestion about a program. This is why the official design is more disciplined than ask the model for ideas. Ideas are cheap. Executable candidate artifacts are different. They can be run. They can fail. They can be stored. They can become parents. They can be compared against other candidates. The loop turns model output into an object the system can govern. That is also why agent is too loose a word for this part of the story. An agent label tells you almost nothing about authority, memory, editable surface, or evaluation. AlphaEvolve is useful because those parts are named and separated. The prompt builder does not do the evaluator's job. The evaluator does not do the database's job. The database does not replace the model. The model does not get to declare success. The machine works because each component has a bounded responsibility. That boundedness is what lets the system be improved later. If a run fails because the parent sampler chose stale candidates, that is a sampler problem. If it fails because the evaluator missed a property, that is an evaluator problem. If it fails because the model proposed invalid code, that is a proposal problem. The architecture gives failures an address. That address is what makes later improvement possible. Without that address, the next run can only try harder. With it, the next run can change the part that actually failed. That is the difference between repetition and repair. The power is not in any one step. The power is in the closed loop. If the model generates a useless diff, the evaluator catches it. If the model generates a small improvement, the database can keep it. If different candidate families score well in different niches, the search can keep those lineages available for later prompts. If the prompt needs better context, the prompt sampler can build from scored ancestry instead of from a blank instruction. That is what separates this from most agent workflows. An agent workflow often says, "Here is the goal, here are the tools, go do the task." AlphaEvolve says something narrower and stronger. Here is the code surface you may change. Here is the evaluator that decides survival. Here is the memory of prior candidates. Now generate another mutation. That is more useful than the usual agent framing, because it makes authority explicit. The system does not need the model to know whether a scheduler heuristic is good. It needs the model to propose a candidate that can be tested by the scheduler simulator. It does not need the model to certify a kernel optimization by intuition. It needs the model to propose code that can run, be timed, and be checked for correctness. The LLM produces possible moves. The environment gives the moves consequences. That is the part most AI demos skip. They show generation. They do not show consequence. In legal work, this distinction is the difference between a chat answer and a matter workspace. If a system drafts a paragraph, that paragraph is not yet work product. It has to sit inside a matter. It has to know what source supports it. It has to know whether the client has a preferred posture. It has to know whether a partner already rejected that language. It has to know whether a citation was checked or merely retrieved. The iris operation here is a matter-object lifecycle. A source enters the matter. A passage becomes a source span. A source span supports a claim card. A claim card carries a caveat and confidence state. A draft uses the claim. A reviewer accepts, modifies, or rejects the draft. Only then should that work become reusable state for the next task. If those transitions live only in the lawyer's head, the system has not become a matter workspace. It has become a better notepad. The legal equivalent of the AlphaEvolve loop is not evolve the brief until it wins. That would be fake precision. The legal equivalent is a workflow where each generated object changes the matter state. A research finding becomes a claim card. A claim card links to a source span. A caveat becomes a blocker. A red line records what changed and why. A reviewer state decides whether the next step can reuse the object. The next legal task should not start from a prompt that says, "Remember what we discussed." It should start from the matter state that survived review. That detail is what makes the loop operational. The matter cannot be a folder of documents plus a chat log. It needs typed work objects. A retrieved source is not yet a checked citation. A checked citation is not yet an accepted claim. An accepted claim is not yet authorized drafting language. A proposed red line is not yet a reviewer-approved change. Each transition changes what the next step is allowed to reuse. AlphaEvolve makes this visible in code because the child program either enters the database with a score and outputs, or it does not. Legal work needs a softer but equally explicit version of the same state transition. Otherwise, the next prompt has to rediscover the matter from scratch. That is the first full bridge from AlphaEvolve to Iris, not the domain, the architecture. The evaluator is where AlphaEvolve gets its discipline. But we have to be careful with this word. The evaluator is not truth in the abstract. It is not a philosopher. It is not a judge of all possible value. It is a human-defined scoring function inside a domain where candidate quality can be made machine-gradable. That boundary is why AlphaEvolve can be so aggressive. If a candidate breaks the code, it fails. If a candidate produces the wrong output on randomized tests, it fails. If a scheduler heuristic strands more resources, it fails. If a kernel is slower, it fails. If a mathematical construction violates the property being checked, it fails. The system can explore because failure is cheap enough to detect. Bad ideas are not catastrophic. They are just candidates that do not survive. The paper also shows that evaluation is not always one blunt test. AlphaEvolve can use evaluation cascades. That means a candidate does not have to receive the most expensive evaluation immediately. A broad, cheaper check can filter obvious failures. More expensive checks can be reserved for candidates that survive the early gates. This matters because some evaluations take real time, real accelerators, or real simulation budget. The cascade is a resource management mechanism. It asks a practical question. How much evidence does this candidate deserve? A broken candidate should not consume the same evaluation budget as a promising one. A candidate that passes a simple correctness check may deserve a runtime measurement. A candidate that performs well on a training set may deserve evaluation on held-out inputs. The loop is not just score everything. It is spend evaluation where it can change the search. The evaluator can also return more than one score. That matters because even machine-gradable tasks can have more than one version of good. A candidate might be correct but slow. Another might be fast but brittle. Another might be simple enough to deploy. Another might work well on one input shape and poorly on another. AlphaEvolve can use multiple scalar metrics where the user has defined them. The scores are still machine-generated measurements inside the evaluatable world, but the system does not have to pretend one number captures every useful property. The official paper also allows richer feedback than a single number. In some applications, desirable properties are hard to capture perfectly in the user-provided evaluation function. AlphaEvolve can use LLM-generated feedback as an additional signal. That point needs a boundary. LLM feedback is not a replacement for the evaluator. It is not a license to turn vague preference into truth. It is an auxiliary way to give the next prompt more useful information when the machine-gradable score does not describe every relevant property. The hard floor remains execution, checking, and user-defined evaluation. This changes how we should think about hallucination. It is tempting to say AlphaEvolve solves hallucination. That is too broad. A better statement is this: AlphaEvolve reduces the damage from LLM mistakes in domains where generated candidates can be executed, checked, and scored. The model can hallucinate a bad change. The loop does not have to believe it. That is a narrower claim. It is also the useful claim. Most knowledge work does not have this luxury. Legal work especially does not. A legal answer can be wrong because it cites the wrong authority. That can be checked. It can be wrong because it drops a controlling exception. That can sometimes be checked if the exception is preserved as a separate object. It can be wrong because it misjudges litigation posture, business risk, client preference, jurisdictional nuance, or the partner's instruction. Those are not single scalar tests. So if a legal AI system claims to be self-improving, without showing you the evaluator, the review state, and the audit path, you should be skeptical. The weaker the evaluator, the more important the workflow state becomes. That is why Iris should not be positioned as a universal legal evaluator. The stronger claim is more grounded. Iris can preserve the evidence, the caveat, the source, the reviewer decision, the redline scope, and the matter context so a lawyer can govern the work. The legal analog to an evaluation cascade is not one score. It is a sequence of review gates. First, is there an actual source? Second, does the quote support the claim? Third, is the jurisdiction right? Fourth, does the procedural posture match? Fifth, does the draft stay inside the authorized redline scope? Sixth, does the answer respect privilege and client instructions? Seventh, has a reviewer accepted this conclusion for this matter? Those gates do not collapse into one number. They create a governed path. A claim can pass the quote gate and fail the jurisdiction gate. A red line can be textually clean and still fail the authority boundary. A memo can be useful as a draft and still not be approved as work product. The cascade also controls review cost. A legal team should not spend senior lawyer attention on every object at every stage. A candidate quote can be checked against the source before it enters a memo. A proposed red line can be checked against the authorized edit zone before anyone debates style. A privilege-sensitive source can be flagged before it is mixed into a broader draft. A jurisdiction mismatch can block a claim before it becomes part of a client-facing answer. That is not replacing judgment. It is protecting judgment from avoidable cleanup. The audit trace is what makes the gate useful after failure. If a claim fails because the quote does not support it, the matter should show the broken quote edge. If a red line fails because it crosses a locked clause, the matter should show the boundary. If a reviewer rejects a conclusion, that rejection should become reusable state instead of a forgotten comment in a chat. This is where legal AI should be stricter than ordinary software demos. The user should not have to ask, why did it say that? The matter should already contain the answer path. The source edge, the caveat, the reviewer instruction, and the redline boundary should be first-class objects. When something fails, the failed object should point to the gate it failed. That is how a legal team learns from the failure instead of merely correcting the final paragraph. This also explains why citation verification alone is not enough. A checked quote can still be used for the wrong proposition. A valid case can still come from the wrong jurisdiction. A correct statement of law can still be wrong for the client's posture. The review path has to preserve the type of failure, not only the fact that something failed. A legal workflow that cannot distinguish those failures will train the team to distrust all of them equally. The point of state is to avoid that flattening. A quote failure needs a source fix. A jurisdiction failure needs a research fix. A redline authority failure needs a drafting boundary fix. A reviewer rejection needs a matter position fix. Different failures need different remedies. That is why the gate has to preserve the failed object's type. Otherwise, every correction becomes manual investigation. That is exactly the work the system should reduce, not by making the lawyer less responsible, but by keeping the evidence of each gate visible enough that responsibility can be exercised quickly. The gate is useful only if its result travels with the object. State is the carrier. That is the right legal translation of evaluator discipline, not machine-scored law, reviewable legal state. In AlphaEvolve, the evaluator decides which code candidates survive. In Iris, survival is more often a governed review path. A claim can survive review only when its authority, caveat, scope, and reviewer state remain attached. A draft change can survive review only when it is within scope. A caveat survives handoff because it is a separate object, not a sentence inside a summary. A final answer can be trusted only when a reviewer can trace it. That is not as clean as a kernel benchmark. It is better suited to law. The official paper also makes a practical model choice that is easy to miss. AlphaEvolve uses an ensemble of Gemini 2.0 Flash and Gemini 2.0 Pro. That is not just a procurement detail. It is part of the search design. A search loop needs volume. If every mutation is expensive, the system cannot explore enough of the space. Gemini Flash gives the loop a high-throughput proposal lane. It can generate many candidate changes quickly, which matters because most candidates should not survive. That last sentence is the economic heart of the design. In a search system, failure is not an exception. Failure is the expected background rate. Most mutations will not be the breakthrough. Some will not run. Some will run but score poorly. Some will improve one dimension while breaking another. If each of those attempts costs the same as the most expensive reasoning path, the search budget collapses before the system has explored enough of the space. Using the strongest model for every sample can feel clean from a product standpoint. It is usually wrong for search. The loop needs many cheap shots and some expensive jumps, but search also needs jumps. Some improvements do not come from another small local patch. They require a stronger proposal, a different decomposition, a better abstraction, or a more coherent rewrite. Gemini Pro supplies that higher capability lane. It is slower, but it can produce proposals that move the search into a better region. The risk goes both ways. If the system uses only the cheaper lane, it may explore locally and miss structural moves. If it uses only the stronger lane, it may spend too much budget on candidates that still need to be tested and discarded. The search needs a routing policy because intelligence is not one uniform substance poured over every step. There is proposal intelligence. There is evaluation intelligence. There is memory selection. There is rewrite authority. There is final review. Each has a different cost and a different failure mode. This is the same reason the system supports both targeted diffs and full rewrites. Sometimes the right move is a small patch. Sometimes the right move is to change the shape of the program. The architecture does not pretend one mode is always best. It routes. That is a serious design principle for legal AI too. A legal platform should not spend the same kind of intelligence on every operation. Extracting entities from a contract, checking a citation, drafting a clause, comparing red lines, synthesizing a research memo, and reviewing a final answer are different jobs. If every job goes through the same monolithic reasoning path, cost rises and control falls. If every job goes through the cheapest path, the system misses the moments where judgment matters. In Iris, the useful pattern is routed work. Routine extraction can be cheap and structured. Citation checking can be strict. Drafting can use matter context. Review can pull source, caveat, instruction, and prior redline state into one inspectable surface. Make that concrete. Entity extraction from a contract should not require the same reasoning budget as deciding whether a limitation of liability clause should change under a specific negotiation posture. Citation checking should be strict and evidence-facing, not creative. Drafting should use the matter's prior state, the client's preferred position, and the relevant source material. Document comparison should preserve the accepted branch, the rejected branch, and the reason for the difference. Final review should collect the source, caveat, reviewer instruction, redline scope, and audit trail in one place. If all of those operations are hidden behind the same chat box, the user cannot tell whether the system is spending attention in the right place. Iris should make the route inspectable. The work mode should match the legal task. That is how routing becomes governance rather than internal plumbing. The payoff is not just lower cost. It is better control over where the system spends attention. That is the operational bridge. Route the right work to the right mode, keep the result attached to matter state, and make the next step inherit what was checked. This is also where rerun cost enters the story. If a citation check fails, the system should not rerun the entire research workflow from zero. It should rerun the affected claim, the source edge, and the dependent paragraph. If a redline comparison finds that one clause crossed a locked boundary, the system should not discard the whole draft. It should isolate the unauthorized change, preserve the approved changes, and route the disputed clause to review. If final review finds that the memo used the wrong procedural posture, the system should not lose the extracted authorities and quotes. It should update the posture field and regenerate only the parts that depended on it. That is the payoff of routed work tied to matter state. The system spends less effort repeating work it already inspected and more effort where the matter actually changed. In a long legal matter, that difference compounds. The platform becomes useful not because one answer was impressive, but because the 10th answer does not start from the same ignorance as the first. That is the legal equivalent of throughput. Not just more generated text per minute, but fewer wasted reruns, fewer repeated source checks, fewer rediscovered caveats, and fewer reviewer cycles spent explaining the same boundary again. The routing layer should make those savings visible as work avoided, not just tokens avoided. That is a better product promise because it is tied to the matter itself. If the system can show that a follow-up reused the checked citation, preserved the approved redline, and only reran the disputed posture analysis, the lawyer can understand why the second pass was faster and safer. The route becomes part of the work product. A matter team should be able to say, this paragraph came from research mode, this citation passed verification mode, this clause came from drafting mode, and this conclusion passed review mode. Otherwise, routing stays invisible and ungovernable. The legal team needs route provenance. AlphaEvolve did not come from nowhere. DeepMind had already shown a related idea with FunSearch. Use language models and evolutionary search to discover useful programs. FunSearch was important because it showed that LLMs could help search for mathematical and algorithmic objects instead of only writing final answers. But the official AlphaEvolve paper is explicit about the next step. FunSearch was narrow. AlphaEvolve expands the surface. FunSearch evolved a single function. AlphaEvolve can evolve an entire code file. FunSearch evolved roughly 10 to 20 lines of code. AlphaEvolve can evolve hundreds. FunSearch worked in Python. AlphaEvolve is designed for any language. FunSearch needed fast evaluation on a CPU. AlphaEvolve can spend hours on evaluations, run them in parallel, and use accelerators. FunSearch used millions of LLM samples. AlphaEvolve can work with thousands. FunSearch used smaller code-focused models. AlphaEvolve benefits from state-of-the-art models. FunSearch used minimal context. AlphaEvolve uses rich prompts with previous solutions, scores, feedback, instructions, relevant documents, and meta-prompt evolution. FunSearch optimized a single metric. AlphaEvolve can optimize multiple metrics. FunSearch showed that LLM-guided evolution could discover useful programs. AlphaEvolve moves that pattern onto a broader controlled work surface. The difference is not only scale, it is control over the shape of the work. A single evolved function is easier to reason about. It is also a narrow intervention. Many valuable systems do not expose their bottleneck as one tiny function. The useful change may sit across a loss function, an initializer, a schedule, a representation, a heuristic, and the way evaluation results are fed back into the next prompt. That is why full-file evolution matters. It gives the system room to change more than the obvious local patch, but it also creates risk. The more surface area the model can edit, the more important the scaffold becomes. The user has to define what can change, what must remain fixed, and how the evaluator will catch illegal or useless moves. Parallel evaluation pushes the same trade-off from another direction. If candidate evaluation takes time, the system can use parallel workers or accelerators to reduce wall clock delay. That does not make evaluation free. It changes the throughput geometry. The loop can explore more candidates per unit of time, but it still needs the evaluator and database to decide what the extra exploration means. The obvious early version is, let the model tweak a small function and keep what scores well. That is powerful, but it hits a wall. Real systems are not one small function. They have scaffolds, interfaces, hidden constraints, deployment requirements, and competing definitions of good. If the editable surface is too small, the system can make local improvements while missing the global shape. If the context is too thin, the model can produce syntactically valid mutations that do not understand the problem. If evaluation must be tiny and fast, many real engineering tasks are out of scope. If there is only one metric, the system can optimize something that looks good in isolation and fails in deployment. AlphaEvolve changes those conditions. It lets the user mark blocks of code that can evolve while the surrounding code acts as a scaffold. It can accept targeted diffs when a local change is enough. It can allow full rewrites when the system needs a larger jump. It can optimize code in the language engineers actually use. It can use larger evaluation budgets. It can keep multiple scores. Each of those changes expands the class of problems without removing the need for boundaries. Any language support means the system can operate where the real artifact lives, not only where a benchmark is convenient. Rich context means the model can see instructions, previous programs, outputs, and feedback. Meta-prompt evolution means even the way the system asks for proposals can be improved in some settings. Multiple metrics mean the database can preserve candidates that are valuable for different reasons. But every expansion also creates a new failure mode. More context can introduce stale assumptions. Larger edit surfaces can break invariants. Parallel evaluation can waste budget if the sampler is poor. Multiple metrics can preserve noise if the scores do not express what the user actually cares about. The point is not that bigger is automatically better. The point is that broader systems need more explicit control. Deployment becomes more plausible when the artifact, edit authority, evaluation budget, and score boundaries are visible. That is also the legal lesson. In a legal document, the system cannot be allowed to rewrite everything just because it can generate text. Some clauses are locked. Some language is editable. Some changes require approval. Some changes are allowed only if they preserve a defined term, a fallback clause, a jurisdictional carve-out, or a client position. A useful legal AI system needs scoped authority. That is why the redlining analogy is strong. The point is not that Iris should mutate a contract until a score improves. The point is that a real document workflow has a scaffold. It has edit zones. It has locked zones. It has approval gates. It has reviewer state. It has a memory of why language was changed or preserved. In a word workflow, this should be visible as authority zones. Editable text is one zone. Locked language is another. Language that can be proposed but not accepted without approval is a third. Definitions, cross-references, fallback provisions, and jurisdictional carve-outs create dependency zones. A change in one place can silently break another. A legal AI system that treats the whole document as a flat text field will eventually make an unauthorized move. Iris should treat the document more like AlphaEvolve treats the editable code surface. Not because contracts are code, but because both require controlled modification. The system needs to know what it may touch, what it must preserve, what requires review, and what prior decision explains the boundary. That is why the FunSearch comparison matters for the legal translation. The lesson is not make the editable surface as large as possible. The lesson is make the editable surface explicit. Small changes need boundaries. Large rewrites need stronger boundaries. Iris should let the legal team see which kind of change is being proposed before the change becomes part of the matter. The same rule applies across documents. If a term sheet, purchase agreement, disclosure schedule, and side letter all depend on the same defined concept, a local red line can have cross-document consequences. A matter-centric system has to surface those dependencies before accepting the change. When Iris works as a matter-centric platform, the prompt is not the control surface by itself. The matter is the control surface. The document, the source, the prior review, the draft branch, and the approval state all constrain what should happen next. That is the difference between a text generator and a legal work system. AlphaEvolve shows this at the engineering level. Controlled mutation beats unconstrained generation. Legal work needs the same discipline, adapted to law. The prompt in AlphaEvolve is not just a bigger bag of text. That matters because the obvious answer to every context problem is to make the context window larger. More room helps, but more room is not the same as memory. If you pour every prior attempt into the prompt, the model gets more material, but the system still has to decide what that material means. Which candidate was apparent? Which candidate scored well on a secondary metric? Which failure came from syntax? Which failure came from the evaluator? Which old program is useful because it solved the same subproblem in a different way? A raw transcript cannot answer those questions. AlphaEvolve's prompt sampler is doing a more specific job. It builds prompts from selected prior programs, scores, feedback, instructions, and explicit context. The previous work is not present merely because it happened. It is present because the database and sampler chose it for the next mutation. The official paper is careful about what goes into that context. It can include the problem statement. It can include fixed human-written instructions. It can include previous programs. It can include rendered evaluation results. Not only the score, but what happened when the program ran. It can include feedback that helps the model understand why one candidate is worth building from and another is not. It can include optional background knowledge supplied by the user. That is a different geometry from paste in the whole transcript. The sampler is not trying to maximize text volume. It is trying to build a useful local world for the next mutation. If the prompt carries too little, the model proposes changes without enough context. If it carries too much, the important signal gets buried. If it carries the wrong prior work, the search can become stale. The hard problem is selection. That is the difference between history and memory. History says, here is everything that happened. Memory says, here is what should affect the next step. That distinction matters for legal AI. A matter can contain thousands of pages, dozens of chats, multiple drafts, red lines, partner notes, client emails, and research trails. Dumping all of that into context is not matter memory. It is a larger haystack. Matter memory has to select. It has to know that this caveat controls the claim. It has to know that this source span supports the sentence. It has to know that this draft branch was rejected. It has to know that this reviewer instruction applies to indemnity language, but not to governing law language. It has to know what is unresolved. In Iris, that is the point of turning work into structured matter state. The system should not ask the next model to rediscover the matter from raw documents. It should bring forward the specific objects that survived review: claim, source, caveat, confidence, draft state, redline scope, and reviewer note. This is where matter memory differs from ordinary retrieval. Retrieval asks, what documents might be relevant? Matter memory asks, what prior work should control the next step? Those are not the same question. A source may be relevant but not adopted. A caveat may be short but controlling. A reviewer instruction may apply only to one clause family. A rejected draft may be irrelevant to the final answer, but crucial for preventing the system from repeating a bad path. An unresolved question may matter more than 10 pages of already settled background. The system has to carry that structure forward. The payoff is not just speed. The payoff is continuity. The next step begins with the right prior work in the right form. That is the Iris operation for this arc. Selected matter packets, not matter dumps. A follow-up drafting request should receive the source spans, accepted claims, live caveats, reviewer notes, and redline scope that actually constrain the draft. It should not receive a pile of everything that ever happened in the matter and hope the model rediscovers what the team already settled. Think about the difference during a real follow-up. The partner asks, update this argument for the latest draft, but keep the caveat we discussed yesterday. A transcript-based system has to infer what the caveat means. It may find the right sentence. It may find a related but wrong sentence. It may miss the fact that the caveat was accepted only for one jurisdiction and rejected for another. A matter memory system should not guess. It should already have a caveat object with a source edge, jurisdiction field, reviewer state, and scope of use. The prompt for the next task should contain that object because it controls the work, not because it happened to appear recently in chat. This is also how reruns become cheaper. If only the jurisdiction changes, the system should rerun the affected claims and leave the unchanged source checks alone. If only the reviewer note changes, the system should update the drafting posture without re-ingesting every document. Prompt context becomes structured memory when the system can choose the minimum state needed for the next step. There is also a failure on the other side: stale memory. If a prior conclusion was overruled by a later reviewer, it should not keep appearing as live context. If a source was checked and found irrelevant, it should not be revived because its language sounds helpful. If a draft branch was rejected, the system should know whether it was rejected for style, substance, authority, client posture, or privilege. Structured memory is not only about bringing things forward. It is also about leaving the wrong things behind. That is why a matter memory packet needs status, not just content. Live, rejected, superseded, unresolved, approved, blocked. Those words change what the next prompt should do. AlphaEvolve has the cleaner version because scores and outputs attach to candidates. Legal work needs a richer status language because the reasons are legal and institutional, not only numerical. A useful matter system, therefore, needs retrieval with memory labels. It should know the difference between "this document contains the clause," "this clause was used in the prior draft," "this clause was rejected by the partner," "this clause is still unresolved," and "this clause is approved for reuse." Those are all different prompts for the next model. Without those labels, larger context only gives the model more chances to confuse old material with live state. The program database is easy to underestimate because the word database sounds passive. In AlphaEvolve, it is not passive. It is the search surface. Every generation creates candidates. The candidates get scores and outputs. The database and sampler decide which prior work is likely to influence future prompts. That means the stored population shapes the direction of search. If it keeps only the current best candidate, the system can converge too early. That is a familiar failure. A search finds something that works locally, treats it as the winner, and stops preserving other possibilities. The problem is that the best current candidate may be a trap. It may be good because it fits the current scoring path, not because it contains the best long-term structure. The official paper points to ideas from MAP elites and island-based population models. You do not need the full theory to understand the pressure. The system needs exploitation. It should reuse candidates that score well. The system also needs exploration. It should keep different families alive long enough for later mutations to reveal their value. That is why diversity is not decoration. Diversity is a search asset. This is where the MAP elites and island model influence matters at the level of intuition. A population can preserve different kinds of winners. One family may score well because it is fast. Another may score well because it is simple. Another may score well because it handles a corner case. Another may not be the best yet, but it contains a structural move that later becomes important. If the database collapses all of that into the single current champion, the system can become efficient at climbing the wrong hill. The official paper describes a database that stores scored solutions and outputs and can resurface previously explored ideas in future generations. That resurfacing is the difference between storage and search memory. The cost is real. Diversity takes space. It complicates selection. It means the system has to decide which families deserve future attention. But premature convergence has its own cost. The search becomes confident before it has explored enough of the landscape. In a legal matter, the same failure shows up as premature summary. One theory gets written cleanly. Another theory is messier. A caveat is inconvenient. A rejected branch looks like clutter. So a summary collapses everything into the cleanest story. That may feel efficient. It can also destroy the work. If the matter later turns on the caveat, the clean memory has become false. If a partner asks why a clause changed, the rejected branch is suddenly relevant. If a jurisdictional distinction matters, the minority theory becomes the controlling path. Iris should preserve that structure. Not every branch needs to be in the final answer, but important branches should remain inspectable. A matter memory board can hold the current draft, the rejected draft, the reason for rejection, the source that controlled the decision, and the reviewer state that made it official. This is institutional knowledge at the matter level. A later lawyer should be able to ask why the final answer did not use a seemingly favorable authority, and see the reason. Wrong posture, later case limited it. Partner rejected that path, client risk tolerance changed, or the authority belonged to a different jurisdiction. Without that preserved branch, the next person may rearg the same issue from scratch. With it, the matter becomes a searchable decision surface. That is not clutter if the system can retrieve it when it matters. It is institutional memory. That is the iris operation for this arc. Keep alternative theories inspectable without making them final answers. The final work product can be clean. The matter state behind it should remain richer than the final prose. The danger is that clean prose feels like progress. In a long matter, clean prose can be a lossy compression format. The summary says, we should not use that argument. The matter needs to remember why. Was the argument wrong? Was it right but too aggressive? Was it rejected by the client? Was it unavailable in this jurisdiction? Was it preserved for a later fallback? Those are different states. If they collapse into one sentence, the next lawyer loses the decision surface. AlphaEvolve's database is useful because different candidates can remain available for different future pressures. Iris should do the legal analog. Keep theories, caveats, rejected branches, and reviewer reasons available as structured matter knowledge. That does not mean every branch is shown to the client. It means the system does not erase the work behind the final answer. The institutional memory version becomes especially important across a firm. One matter may teach that a certain argument looks attractive, but fails under a particular procedural posture. Another matter may teach that a client prefers a narrower drafting posture, even when a broader clause is legally available. A third matter may contain a partner-approved explanation of why a fallback clause should not be removed. Those are not generic documents. They are decisions. If they are stored only as prose in old work product, the next team may never find them. If they are stored as structured matter knowledge, the system can surface them when a similar pressure appears. That is how institutional knowledge becomes more than search. Search finds text. Institutional memory finds prior decisions with reasons. AlphaEvolve does not preserve a population because every candidate belongs in the final answer. It preserves a population because future search may need different parents. A legal platform should not preserve every matter object because every object belongs in the final memo. It should preserve the decision structure because future work may need the reason a path was accepted, rejected, narrowed, or held in reserve. That decision structure is what lets institutional knowledge survive staffing changes. A new associate can enter the matter and see not just the current answer, but the map of prior choices. A partner can ask why the team abandoned a theory and get the source, caveat, and reviewer reason instead of folklore. A client can change posture without forcing the team to rediscover every discarded path. That is a different product from enterprise search. Search retrieves prior language. A matter system retrieves prior judgment with its constraints. That constraint is the object worth reusing. Without it, prior work becomes just another document to search. With it, prior work becomes a governed precedent inside the matter. That precedent can be reused, challenged, or retired. Search alone cannot do that. State can. That is why the board matters. It keeps prior judgment alive. It prevents rediscovery loops. It saves review time. Single-score optimization is seductive because it makes the world look clean. One score goes up, the system improves, but real deployment is rarely that simple. AlphaEvolve supports multiple user-provided scores. The official paper notes that this can matter even when one metric is the main target, because candidates that perform well under different criteria can have different structures. Those different structures can enrich future prompts and increase the chance of finding better candidates. This is not only a deployment trade-off, it is a memory strategy. If one candidate is the speed winner and another is the simplicity winner, the system can preserve both structures as useful parents. Even if the final target metric is dominant, the secondary score can keep a different family alive long enough to become useful. That is why multiple scores are not just a dashboard. They change what survives. They change what the sampler can show the model later. They change the shape of the search population. There is also a failure mode. Metrics can be gamed. Metrics can conflict. A score can reward the behavior that is easiest to measure rather than the behavior that actually matters. AlphaEvolve still depends on the user defining useful evaluators and scores. Multiple scores give the system more structure. They do not remove the burden of defining what should count. This is also where LLM-generated feedback can help inside AlphaEvolve's boundary. Some desirable properties are hard to express completely as scalar metrics. A candidate may be technically correct but awkward, brittle, hard to interpret, or mismatched to a design preference. The official system can use LLM-generated feedback to enrich the prompt when the numeric score does not describe every relevant property. That feedback is auxiliary. It does not replace the evaluator. It does not turn preference into truth. It gives the next mutation more context, while the machine-gradable evaluation remains the floor. Multiple metrics are not only a way to express trade-offs. They are a way to preserve different kinds of useful behavior. In engineering, one candidate may be fast but complex. Another may be simple but slightly slower. Another may be robust across input shapes. Another may be easier to deploy. If the system sees only one number, it may throw away candidates that would be valuable under a different pressure. That is why a serious optimization system has to remember more than best. It has to remember why something was good. Legal work has the same shape, but the metrics are not clean numbers. A research answer has authority strength. It has jurisdictional fit. It has procedural posture. It has client risk. It has privilege sensitivity. It has deadline pressure. It has reviewer preference. It has business consequence. Those are not one score. If a legal AI system collapses them into a single confident paragraph, it hides the trade-offs the lawyer actually needs to see. In Iris, the useful move is to keep those dimensions visible. A claim can carry authority strength. A draft can carry risk posture. A red line can carry approval state. A memo can expose unresolved questions. A reviewer can decide which dimension controls the next step. Make that visible as a matter board. One column holds authority strength. One holds jurisdiction fit. One holds client posture. One holds privilege sensitivity. One holds deadline pressure. One holds reviewer preference. One holds business consequence. The answer does not need to recite the whole board every time, but the board has to exist so the next decision can use it. This is not slower for the sake of being careful. It is faster because the next decision starts from explicit trade-offs instead of reconstructing them from prose. That is the iris operation for this arc. Preserve the dimensions of legal judgment separately enough that a reviewer can choose which one controls, instead of forcing every trade-off into a single confident paragraph. The single paragraph failure is especially dangerous in legal work because it hides disagreement. A claim can be strong on authority and weak on posture. A clause can be favorable to the client and unacceptable to the counterparty. A strategy can reduce legal exposure and increase business friction. A citation can be controlling but unhelpful under the current facts. If those dimensions are hidden, the reviewer has to reverse engineer the trade-off from prose. If they remain visible, the reviewer can decide. For this matter, client posture controls. For this deadline, procedural fit controls. For this negotiation, red line authority controls. The same claim can move differently depending on which dimension is selected. That is why multimetric thinking transfers as structure, not as scoring law. Iris should not announce one legal score. It should preserve the dimensions that make legal judgment possible. There is a practical reason to keep the dimensions separate even when the final answer is short. A deadline can change the right workflow. With 3 hours left, A team may need the strongest controlling authority and the safest caveat. With 3 weeks left, the same issue may deserve a broader survey and a more aggressive fallback path. Client posture can change the right draft. A risk-averse client and a deal-driven client may both need accurate legal analysis, but they may not want the same first red line. Privilege can change what the system is allowed to show or reuse. Reviewer preference can change which authorities are considered persuasive inside the team. None of that belongs in a single score. It belongs in matter state. This is also where client service improves. When a partner asks for a more conservative posture, the system should not rewrite the entire memo from nothing. It should adjust the risk posture dimension and show which claims, caveats, and red lines are affected. When a deadline moves, the system should show which unresolved questions can no longer be explored deeply, and which authority checks are already complete. The point of keeping multiple dimensions is to make the next decision cheaper to reason about. The interface should make that visible without turning the lawyer into a spreadsheet operator. A compact trade-off panel can show which dimension controls the current step, which dimensions remain live, and which ones are resolved. The user should be able to switch the controlling dimension and see what work changes. That is how multi-metric structure becomes practical legal control rather than another abstract dashboard. It turns the next task into a choice about which dimension controls, not a blind rewrite. That is the practical payoff of keeping the vector visible. It gives the reviewer a control surface rather than a paragraph to decode. The cleanest way to test whether a component is doing work is to remove it. That is what the AlphaEvolve paper does with ablations. The official ablations are not universal proof across every domain. They are run on selected tasks, tensor decomposition for matrix multiplication and lower bounds for kissing numbers. That scope matters. Inside that scope, the result is still important. On both tested task families, removing the evolutionary approach hurts performance. On both tested task families, removing explicit prompt context hurts performance. In the tensor decomposition ablations, the paper also removes metaprompt evolution, full file evolution, and the stronger model lane. Each removal hurts performance in that setting. The scope split has to stay visible. No evolution and no explicit prompt context are tested across the two task families in the ablation figure. The metaprompt, full file, and strong model lane removals belong to the tensor decomposition side. If we compress that into every component was proven everywhere, we lose the paper's discipline. The right claim is narrower. In the tested settings, removing these parts made the system worse. That is enough. It shows the system is not merely a large model receiving a prompt. The architecture is doing work. That pattern is the argument. It says AlphaEvolve is not just a big model being lucky. The loop matters. The context matters. The editable surface matters. The stronger model lane matters. The database and evolutionary pressure matter. That is why the word agent is too vague here. If you call everything an agent, you lose the ability to say which parts are doing work. AlphaEvolve is valuable because the parts have jobs. The evaluator filters. The database preserves. The prompt sampler focuses. The model mutates. The evolution loop accumulates. The ablations matter because they show those jobs are not cosmetic, at least in the tested settings. That gives the viewer a useful test for any AI workflow. Ask what breaks when a component is removed. If removing memory changes nothing, the memory was decorative. If removing citation grounding changes nothing, the citations were decoration. If removing reviewer trace changes nothing, the workflow was not actually reviewable. If removing redline scope changes nothing, the system was never respecting drafting authority. This is the same standard Iris should be held to. Matter memory is not a feature if removing it makes every question start cold. Citation grounding is not a feature if removing it makes claims unreviewable. Reviewer trace is not a feature if removing it makes failures impossible to localize. Redline scope is not a feature if removing it lets the system change language it had no authority to change. The question for legal AI is not, does it have a chat interface? The question is, what breaks when you remove the state? If nothing breaks, it was decoration. If the workflow collapses, it was architecture. That is the iris operation for this arc. Failure localization by removal. The matter board should make it obvious which part of the workflow failed. Did the source fail? Did the caveat fail? Did the reviewer state fail? Did the redline boundary fail? Did the audit trace fail? Without that address, every failure becomes a general loss of trust. This is also how teams decide what to improve. If the failure came from retrieval, improve retrieval. If it came from citation verification, improve the quote source edge. If it came from redline scope, improve the authority map. If it came from reviewer handoff, improve the reviewer state transition. If it came from matter memory, improve what state gets selected for the next task. The ablation mindset forces specificity. It prevents the vague post-mortem. The AI was wrong. In a serious workflow, wrong is not enough. The team needs to know which component failed and what state would have prevented it. That is how a legal AI platform becomes governable over time. Ablations also protect against false product claims. If a vendor says it has memory, ask what breaks when memory is removed. If a vendor says it has citations, ask whether the claim becomes blocked when the source edge is missing. If a vendor says it has review, ask whether reviewer decisions actually change the next task. If a vendor says it has document redlining, ask whether unauthorized edit zones stop the system or merely appear in the UI. The AlphaEvolve ablation habit gives a vocabulary for pressure testing legal AI features. Features are cheap to list. Load-bearing state is harder to fake. The legal removal test can be concrete. Remove matter memory and the follow-up starts cold. Remove citation grounding and the claim cannot be reviewed. Remove reviewer trace and no one knows why the draft changed. Remove redline scope and the system can alter language it had no authority to alter. Remove audit trace and every failure becomes a general suspicion about the whole system. That is the difference between a feature list and an architecture. The same test should be used before trusting any final answer. If the answer cannot show what source grounded it, what caveat limited it, what reviewer state approved it, and what redline boundary constrained it, then the final paragraph is doing too much unsupported work. The architecture should make unsupported work impossible to miss. This also makes quality improvement concrete. The team can improve the weak component instead of blaming the whole model. That is why the ablation lesson belongs before the results. It teaches the viewer how to read the wins, not as isolated miracles, but as consequences of a system whose parts have jobs. It also teaches restraint. A component can be load-bearing in one tested setting and still need validation elsewhere. That is the same discipline we need for legal AI. Prove the workflow where it is actually used. Do not market the component as universal until the removal test has been run in the workflow that matters. That is the guardrail. It keeps the claim honest. It also keeps repair possible. That matters later. Now the results matter, but they only matter if we keep their shape. The easiest way to ruin the AlphaEvolve story is to turn it into a headline. DeepMind made matrix multiplication faster. That is not precise enough. The official result is narrower and more interesting. Matrix multiplication can be represented as a tensor decomposition problem. If you can find a lower-rank decomposition, You can reduce the number of scalar multiplications needed for a specific matrix multiplication target. That sentence compresses a lot of history. For decades, matrix multiplication has been a place where tiny rank improvements matter because the operation sits under so much computation. The object AlphaEvolve is searching for is not a faster implementation of one loop in one library. It is an exact decomposition for a specified multiplication tensor. Rank is the key word. Lower rank means fewer scalar multiplications for that target, but the target matters. The size matters. The field matters. Exactness matters. The paper describes rounding elements to integer or half-integer values during evaluation to avoid numerical error and to encourage exact decompositions. That is a much more constrained claim than the AI made matrices faster. That is the world AlphaEvolve was operating inside. It was not making every matrix multiplication in every program magically faster. It was searching for exact algorithms for specified tensor shapes. Across 54 matrix multiplication targets, AlphaEvolve matched the best known rank in 38 cases. It improved the state of the art in 14 cases. It fell behind in 2 cases. The 2 failures matter as much as the wins. They keep the table honest. They show that AlphaEvolve is not a blanket domination machine. It is a search method that can match, improve, or miss depending on the target. That is exactly why the full table is more credible than a headline. That mix is important. A real result does not need to pretend every row is a win. The famous part is the 4x4 complex-valued case. Recursive Strassen gives rank 49 over any field. The sub-49 characteristic 0 boundary was the open one. AlphaEvolve found a rank 48 algorithm for multiplying 2 4x4 complex-valued matrices. There is a caveat inside that history. Some algorithms with fewer than 49 multiplications were known in narrower settings, but they were not tensor decompositions of the matrix multiplication tensor and could not be recursively applied to larger matrices. AlphaEvolve's claim is about the tensor decomposition path for the 4x4 complex-valued case. That is a serious mathematical result. It is also a bounded result. It is about a specific decomposition, in a specific setting, with exactness checks. It does not mean a 2% speedup across all matrix multiplication. It does not mean deployment is automatic. It does not remove the engineering work of turning a discovered algorithm into a useful implementation. Even an exact algorithm has to be situated before it becomes operational. Can it be implemented efficiently? Does it help at the sizes the system actually uses? Does it interact well with memory movement? Does the hardware support the required operations efficiently? Those questions are outside the rank table. They do not weaken the result. They define the path from mathematical object to engineering value. That boundary is not a weakness. It is what makes the claim trustworthy. This is where legal AI usually goes wrong. It turns a bounded result into a broad statement. The case supports our position. Which case, which holding, which jurisdiction, which procedural posture, which quoted language, which caveat, which counter-authority. The legal equivalent of a matrix result is not a confident paragraph. It is a claim with its scope attached. In Iris, a serious research answer should behave like that. The claim card should carry the source span, the jurisdiction, the caveat, the confidence level, and the reviewer state. If the claim is narrow, the system should preserve the narrowness instead of sanding it down into a stronger sentence. The Iris operation for this arc is claim release. A legal claim should not leave the research board until the holding, jurisdiction, procedural posture, caveat, and counter-authority fields have been checked. If the result is narrow, the answer should stay narrow. If the authority is useful only under one posture, The posture should travel with it. The lesson is not AI found a result. The lesson is a result becomes usable when its boundary survives the journey into the final work product. The boundary is part of the result. Legal claims need the same discipline when they appear in a memo. Suppose a case says a contractual notice provision was enforced under one state's law after a specific course of dealing. A summary might turn that into, "Courts enforce notice provisions." That sentence may be directionally true and still too broad to use. The matter needs the narrower object: jurisdiction, facts, procedural posture, holding, quoted language, caveat, and counter-authority. Only then can the lawyer decide whether the case supports the current position. The matrix table teaches the same habit. Count the wins, count the misses, name the target, preserve the exactness condition, keep deployment separate from discovery. Iris should make overbroad legal claims fail at the same place a bad headline fails. The scope field is missing. That is why this arc should not rush through the 54 target table. The table is a teaching object. It shows matched cases, improved cases, and behind cases together. It shows that exact algorithms can still be target-specific. It shows that one famous row, the 4x4 complex-valued rank 48 result, should not absorb the whole story. A legal research table should work the same way. Favorable authority, limiting authority, distinguishable authority, and unresolved authority should appear together before the final conclusion chooses its path. The final claim can be concise only after the comparison has been honest. This is also why matched results matter. Matching the state of the art is not a failure if the task is hard. It tells us the search can recover known best structure across many targets. Improving 14 targets is meaningful because it sits beside 38 matches and 2 misses. That full distribution is what a legal answer should imitate. It should show where authority supports the position, where it only matches the baseline understanding, and where the available authority is weaker than hoped. The table also teaches restraint in thumbnails and titles. The hook can mention a 56-year boundary or a rank 48 result, but the script must keep returning to the full distribution. The viewer should leave remembering not just the win, but why the win was credible. Exact target, exact count, exact caveat. The same restraint should govern upload metadata and article conversion later. No blanket matrix speed claim, no unsupported percentage claim, no deployment claim without engineering caveat. The legal analog is just as strict. No case supports us claim without the holding and caveat. No risk is low claim without the assumptions. No red line is safe claim without scope and reviewer state. This is how a legal platform avoids turning narrow evidence into broad confidence. It forces the claim to carry its limits. The limit is not an apology. It is what makes reliance possible. Scope is usable evidence. The open math section has a different lesson. In more than 50 open problems, AlphaEvolve matched the best-known construction about 3/4 of the time and surpassed it about 1/5 of the time. Those are strong numbers, but the mechanism matters more than the percentage. For many of these problems, AlphaEvolve was not producing a polished proof from scratch. It was producing constructions, objects, configurations, search heuristics that could improve an existing best object. The official paper describes an iterative refinement strategy for many mathematical problems. Each generation evolves a program representing a search heuristic. That heuristic receives a time budget and often starts from the best construction found by the previous best heuristic. The goal is not merely to output a final answer. The goal is to discover heuristics that improve already strong objects. That is a different kind of progress from write a proof. It is closer to building a sequence of search tools. Early heuristics may make large gains from random or simple initial states. Later heuristics may fine-tune near-optimal configurations. The final construction can be the product of a chain of specialized heuristics rather than one monolithic insight. For the kissing number problem in 11 dimensions, the paper reports a configuration of 593 non-overlapping unit spheres touching a central unit sphere, improving the lower bound from 592 to 593. The number is small. The implication is not. In difficult mathematics, progress often looks like one more object that satisfies a hard set of constraints. But construction, checking, and proof are different jobs. AlphaEvolve can search for objects inside a formalized evaluation world. It can produce candidates that pass checks. It can improve lower bounds. It can help mathematicians explore a space that would be brutal to search manually. That still leaves human formulation and validation in the loop. The paper itself points to open problems suggested by external mathematicians and to human expertise in formulating them for AlphaEvolve. That formulation work is part of the result. Someone has to decide how to represent the problem. Someone has to decide what can be evaluated. Someone has to decide whether the discovered object is meaningful. Someone has to check the proof path or the construction certificate. The AI search does not remove that work. It changes what the human can search over. That is the real partnership. The human does not vanish. The human defines the search world, understands the significance, checks the boundary, and decides what the result means. Legal research has the same split. A system can find authorities, extract quotes, compare procedural posture, and assemble a draft conclusion. But a legal answer is not useful merely because it sounds complete. It needs reviewable pieces. Claim, quote, authority, conflict, caveat, procedural fit, reviewer status. In Iris, that structure should remain visible. A research answer should not flatten its evidence into prose and ask the lawyer to trust the surface. It should keep the work inspectable, so a lawyer can see what is source-backed, what is inferred, what remains unresolved, and what changed after review. The iris operation for this arc is the research trace. Quote to authority, authority to claim, claim to caveat, caveat to unresolved question, reviewer status to reusable matter state. If those edges stay visible, a lawyer can distinguish a found authority from a reviewed conclusion. That is the legal version of the AlphaEvolve lesson. Do not confuse an output with a verified result. The most important legal parallel is unresolved status. An AI system may find a case and extract a quote. That is useful. It may assemble a draft conclusion from several authorities. That is more useful. But until a reviewer has checked the fit and accepted the conclusion for the matter, the work should remain in a draft or unresolved state. That status is not bureaucracy. It prevents a found object from masquerading as a final legal position. AlphaEvolve's mathematical outputs gain meaning because they can be checked against the problem formulation. Legal outputs gain meaning because their evidence, inference, and reviewer status remain distinguishable. This is also where human expertise is not a footnote. The paper mentions external mathematicians suggesting problems and advising on formulation. That is not incidental. The search engine needs a world to search. A poorly formulated problem can produce candidates that score well and still miss the human point. Legal work is full of formulation choices. What is the actual issue? Which jurisdiction controls? What posture matters? What facts are assumed? What client objective is real? A legal research system should keep those formulation notes. If the lawyer framed the question narrowly, that framing should travel with the answer. If the client changed the objective, that change should attach to the research path. If a partner said to avoid an aggressive argument, The system should not rediscover that argument as if it were new. The output is only useful if the formulation remains visible. The same principle applies to proof paths. A construction can be promising, checked, or incorporated into a proof. Those states should not blur together. In legal work, a found case, a checked quote, a drafted inference, and an approved conclusion are similarly different. Iris should preserve those states so the team can tell whether it is looking at raw material, reviewed analysis, or final position. That distinction is especially important when the answer moves from research into drafting. A draft can cite a construction-like object, but the reviewer still has to decide whether the object carries the legal conclusion. The system should make that handoff explicit. Research status should not silently become drafting authority. Drafting authority should not silently become final approval. Each step needs a state transition. That state transition is the lawyer's control point. It lets the team use AI-found material without surrendering the distinction between search, analysis, drafting, and advice. Without that control point, every useful construction becomes too easy to overuse. The right status keeps the object useful without pretending it is final. That is the same distinction Iris has to preserve between a research artifact and approved advice. The distinction should survive into the draft, the review comments, and the final matter record. Otherwise, the same authority can be overread in the next drafting pass. The system should keep the conclusion's maturity level attached. That is how research remains useful without becoming overconfident advice. State prevents drift. Iris can help preserve those formulation choices as matter state, but it should not pretend the choices are automatic. That is the line between assistance and authorship. The system can carry the frame. The lawyer remains responsible for choosing it. The Borg scheduling result is the most useful bridge from science to operations, not because the number is large, because the deployment standard is high. Google's Borg scheduler has to place jobs onto machines with finite CPU and memory. Bad placement can strand resources. A machine may have CPU available but not enough memory, or memory available but not the right CPU shape. At fleet scale, small inefficiencies become expensive. The mechanism is easier to see with a simple bin packing picture. A pending job needs a certain amount of CPU and memory. A candidate machine has some CPU and memory free. If the scheduler places jobs poorly, it can leave awkward leftovers. Enough CPU to be useful but not enough memory, or enough memory but not enough CPU. Those leftovers are stranded capacity. AlphaEvolve was used to evolve a heuristic for this scheduling problem. The heuristic scores potential machines for a pending job, but only within the set of machines Borg has already determined are available and capable. That boundary matters because the evolved heuristic is not allowed to decide that an incapable machine is capable. The paper says the discovered heuristic recovered on average 0.7% of Google's fleet-wide compute resources that would otherwise be stranded. The validation path also matters. The paper describes simulator feedback based on historical snapshots of workloads and capacity, an unseen test dataset, and then fleet-wide rollout. Post-deployment measurements confirmed the simulator results. That sequence is the deployment story. Simulation, unseen test, production rollout, production measurement. Without that sequence, the heuristic would be a promising artifact, not an operational result. That is a small percentage attached to a huge system. But the more important line is why this kind of code heuristic was attractive. The paper says AlphaEvolve was chosen over a deep reinforcement learning approach because the code solution offered interpretability, debuggability, predictability, and ease of deployment in a mission-critical system. That is the deployment lesson. The best answer is not always the most mysterious answer. In a production system, the answer has to be understood, debugged, bounded, and rolled out. Legal AI adoption has the same constraint. A partner does not only ask whether the answer sounds right, they ask whether they can inspect the route. Where did this claim come from? Why did the system choose this source? What instruction controlled the draft? Which clause was changed? Which language was outside the red line scope? Which reviewer approved the move? An opaque answer can be impressive in a demo and unusable in a matter. Iris has to win on the Borg standard, not on the novelty standard. The work path has to be visible enough that a lawyer can debug it, predictable enough that a team can govern it, and bounded enough that it can be deployed inside real legal workflows. That is why matter memory, citation grounding, reviewer trace, and redline scope are not nice extras. They are the parts that make the system operational. The iris operation for this arc is deployment trust through inspectable workflow routing. A legal team will not adopt a system because it produced one impressive answer in a demo. It will adopt the system if the route can be debugged, source selected, instruction applied, draft changed, reviewer approved, audit path preserved. The work has to be simple enough to inspect even when the underlying AI is powerful. This is why the Borg example belongs in a legal AI video. It shows that deployment is not only a question of peak performance. The code heuristic was attractive because it could be inspected, debugged, predicted, and rolled out. A deep reinforcement learning approach might be powerful, but if the team cannot reason about it in a mission-critical scheduler, adoption becomes harder. Legal teams have the same adoption filter. They need to know why the system chose a source, why it changed a clause, why it preserved a caveat, and why it routed a question to review. The answer does not have to expose every internal token. It has to expose enough operational structure for a lawyer to govern the workflow. That is the difference between impressive and deployable. For legal work, deployment also includes handoff. The associate hands a draft to a partner. The partner sends comments back. The client changes the business posture. The matter returns weeks later. If the system cannot carry the route through those handoffs, it has not solved the operational problem. It has only helped with one drafting moment. The Borg lesson is that real systems live under continuity pressure. A scheduler heuristic has to behave across the fleet, not only in a notebook. A legal AI workflow has to behave across the matter, not only in one chat session. That is why interpretability is not a cosmetic preference. A legal team needs to explain its work to itself before it can explain it to a client, court, regulator, or counterparty. If the system cannot show the route, the human has to reconstruct it manually. That reconstruction cost is exactly what matter-centric AI should reduce. The workflow also has to preserve production evidence. If a simulator result and production rollout disagree, the team needs to know where the gap appeared. In legal work, if a draft that looked safe in isolation fails in partner review, the matter needs to know whether the failure came from facts, client posture, redline scope, or authority. Deployment trust comes from seeing the gap. That gap record should survive handoff. Otherwise, every new reviewer starts by asking the same question: what happened here? In Iris, the analogous record is the difference between a draft note and an audit path. A draft note says what the system did. An audit path shows the source, instruction, route, reviewer action, and resulting matter state. That audit path is what lets a legal team deploy AI in repeated work. If every answer has to be manually reconstructed, the system may save drafting time but lose review time. If the path is preserved, review becomes targeted. The target is not just faster first drafts. It is faster reviewed work. That distinction matters because legal teams measure trust at handoff, not at generation. If the handoff loses the route, the next reviewer has to rebuild trust manually. If the handoff carries the route, review can start at the actual disputed point. That is what makes deployment repeatable across a legal team, rather than dependent on one user's memory. Repeatability is the difference between an assistant and infrastructure. For a law firm, infrastructure is what survives the handoff from one reviewer to another. That is why reviewer trace belongs in the product story. It makes trust portable. The same applies when a client team changes. A new reviewer should not inherit only a polished draft. They should inherit the route that made the draft defensible. That route is what lets the work survive turnover, delay, and escalation. The remaining engineering results all point to the same hidden truth. Most of the cost of a serious system lies below the surface. Users see the model. They do not see the kernel. They do not see the tiling heuristic. They do not see the hardware description. They do not see the compiler intermediate representation. But that is where a lot of the performance is won or lost. For Gemini kernel engineering, AlphaEvolve optimized tiling heuristics for a matrix multiplication kernel used in training. The objective was actual runtime on real TPU accelerators. The paper reports an average 23% kernel speedup across the measured kernels over an expert-designed heuristic, and a corresponding 1% reduction in Gemini's overall training time. Kernel tiling is a hidden layer of performance. The kernel has to divide a large matrix multiplication into tiles that balance computation and data movement on accelerator hardware. A poor tiling decision can waste time even if the mathematical operation is unchanged. Engineers can auto-tune or handcraft heuristics, but that process is expensive and has to adapt to input shapes and hardware realities. AlphaEvolve's target was not a vague, make Gemini faster. It was a tiling heuristic for an important kernel, evaluated by actual runtime on real TPU accelerators. 1% overall is not a small thing when the system being trained is enormous. The paper also reports that the optimization time dropped from several months of dedicated engineering effort to days of automated experimentation. That is a different kind of gain from the speedup itself. It changes the engineering cycle. The team can reach a performant heuristic faster, and engineers can spend more time on higher-level optimization problems. But again, the claim has shape. It is not AlphaEvolve made Gemini 23% faster. It is a kernel-level speedup in a specific optimization setting, with a smaller effect on total training time. For TPU circuit design, AlphaEvolve suggested a Verilog rewrite for a key arithmetic circuit. TPU designers validated the correctness. The paper also says the same improvement was independently caught by downstream synthesis tools. That caveat has to stay attached. It keeps the result honest. It says AlphaEvolve found a useful source-level optimization early in the design flow, not that it single-handedly invented a chip breakthrough no other tool could find. For flash attention and XLA intermediate representation, AlphaEvolve optimized compiler-generated code for a specific inference scale configuration. The paper reports a 32% speedup for the flash attention kernel configuration and a 15% speedup in pre- and post-processing. Human experts confirmed correctness. Those three examples live at different layers. Kernel tiling changes how a computation is scheduled on hardware. RTL rewriting changes source-level hardware description. XLA-IR optimization changes compiler-generated intermediate representation for a specific configuration. Putting them under one headline hides the most important thing. AlphaEvolve can work where the artifact is editable, evaluation is executable, and correctness can be checked. AlphaEvolve is not only useful at the visible answer layer. It can operate where the work is encoded as editable artifacts, where evaluation is executable, and where the result can be checked before it is trusted. That is the hidden layer lesson for Iris. A legal memo is the visible output. Under it sits retrieval, source extraction, quote selection, issue framing, jurisdiction filtering, draft assembly, redline control, reviewer instruction, and audit trace. If those layers are invisible, the final memo becomes harder to trust. If those layers are structured, the final memo becomes easier to inspect, rerun, challenge, and improve. The Iris operation for this arc is hidden operation trace. A final memo should be able to open its own provenance. Which sources were retrieved, which quotes were extracted, which jurisdiction filter ran, which document comparison controlled the red line, which reviewer instruction constrained the draft, and which audit trace explains the final answer. The user does not need that trace every second, but the trace must exist when the work is challenged. The hidden layer analogy also helps explain why a legal AI platform cannot be judged only by the final prose. Two systems can produce similar-looking memos. One may have retrieved sources, checked quotes, tracked caveats, compared drafts, preserved reviewer notes, and kept an audit path. The other may have generated a smooth answer from a pile of context. The surface can look similar. The operational value is different. The first system can be challenged and repaired. The second system has to be relitigated from scratch. This is why hidden structured work matters. The month-to-days kernel result is important here because it is not just a speed number. It says the optimization workflow itself changed. The team moved from months of dedicated engineering effort to days of automated experimentation for that heuristic search. Legal work has its own version of cycle time. How long does it take to update a memo when the facts change? How long does it take to compare a new draft against the partner-approved position? How long does it take to rerun citation checks after a new authority appears? How long does it take to explain why a clause changed? The final memo is only one artifact. The cycle time around the memo is where a lot of the value lies. Iris should make that cycle time shorter by preserving hidden operations as reusable state. That is also where the native word workflow matters. The final legal artifact often lives in a document, not in a chat transcript. If track changes, comments, defined terms, and clause boundaries live outside the AI system, the system cannot fully govern the workflow. The hidden trace has to connect to the document where legal work actually happens. Otherwise, the platform may understand the memo in chat and lose authority in Word. The same applies to document comparison. A hidden operation trace should not stop at draft changed. It should show which source drove the change, which prior version it replaced, which track change remains pending, and which reviewer comment resolved it. That is how the hidden layers become usable inside the document workflow rather than trapped behind the chat surface. The final answer is only the visible top of that stack. The value is in the stack remaining available after the answer is delivered. That is why hidden work should be designed for retrieval by the reviewer. If the user has to ask the model to reconstruct its own process from memory, the trace has already failed. The trace has to be stored as state. That stored trace also changes collaboration. An associate can draft from the trace. A partner can challenge one step without reopening every source. A client can ask why a clause moved and receive the source, instruction, and reviewer reason rather than a vague explanation. A later matter can reuse the approved reasoning without copying the old memo blindly. This is the legal analog of optimizing below the surface. The visible output improves because the hidden workflow becomes structured enough to reuse. The hidden work is not extra decoration around the memo. It is what makes the memo governable. The same idea explains why Iris should not hide all system work behind conversational fluency. The lawyer does not need an engineering dashboard, but they do need enough matter-level structure to inspect the work. Source selected, quote checked, caveat preserved, red line compared, reviewer state applied, audit trace stored. Those are the legal equivalents of the kernel, RTL, and compiler layers. They are below the surface, but they decide whether the surface can be trusted. The user should not have to see every internal operation all the time, but the system has to preserve enough state that the operation can be inspected when it matters. That is how serious AI work becomes institutional work, not by producing a prettier final answer, by preserving the hidden operations that made the answer safe to use. Small percentages get attention because small percentages can be large at scale. That is true. It is also where precision usually dies. The official AlphaEvolve paper reports operational improvements. 0.7% fleet-wide compute recovery for Borg, 23% kernel speedup with 1% overall Gemini training time reduction, and specific flash attention plus pre- and post-processing speedups for a particular configuration. Those are official claims. Dollar estimates are different. If a newsletter translates 0.7% fleet-wide compute recovery into an estimated number of servers or an estimated annual capacity value, that can be useful scenario modeling. It can help a viewer feel scale, but it is not the same kind of claim as the official paper. It depends on assumptions: fleet size, server cost, utilization, power, deployment scope, and whether the recovered capacity offsets new purchases or simply changes scheduling headroom. Those assumptions are not embarrassing. They just have to be visible. An estimate can be useful without pretending to be measured savings. A scenario can help the viewer understand scale without becoming a DeepMind claim. The problem begins when the estimate inherits the authority of the official result while hiding the assumptions that produced it. That is how technical storytelling becomes slippery. The official result says what was measured. The scenario estimate says what the result might imply under a model. The model has inputs. The inputs have uncertainty. The uncertainty has to travel with the number. So if we mention economics, the visual has to label it clearly. Scenario estimate, not DeepMind claim. Back of envelope, not measured savings. That is the same discipline the entire video has been teaching. Keep the source attached. Keep the scope attached. Keep the caveat attached. Legal AI has exactly the same problem. A client wants the answer. A partner wants the risk. A business team wants the economic consequence. Those are not all the same object. If a legal memo says a clause could create material exposure, the system should not silently convert that into a confident dollar number unless the assumptions are visible. If a damages estimate depends on a model, the model has to stay attached. If a risk ranking depends on jurisdiction, posture, or factual uncertainty, that has to stay attached too. The legal version has at least 4 different objects: a quoted authority, a lawyer's inference from that authority, a business assumption about exposure, probability, timing, or client appetite, a scenario estimate that combines the inference and the assumption. If those collapse into one paragraph, the reader cannot tell what is law, what is inference, what is business modeling, and what has been reviewed. That is dangerous because each object fails differently. The authority can be wrong. The inference can be too aggressive. The business assumption can be stale. The estimate can be arithmetically right and strategically useless. The reviewer judgment can change once the client updates the facts. In Iris, this is why matter state matters. The platform should preserve the difference between a quoted authority, a lawyer's inference, a business assumption, and a scenario estimate. They may all appear in the same work product. They should not collapse into one voice. That is the iris operation for this arc, provenance by object type. A matter board should let a lawyer inspect which parts are source-backed, which parts are inferred, which parts are business assumptions, which parts are scenario estimates, and which parts have reviewer approval. The state machine is simple. An authority enters as quoted law. A lawyer or system drafts an inference from it. A business assumption attaches to the inference. A scenario estimate uses the assumption. A reviewer decides whether that estimate belongs in the work product. If any one of those states changes, the estimate should update or lose approval. If the assumption changes, the legal authority did not change. If the authority changes, the business model may still be arithmetically correct but legally unsupported. Those distinctions are what keep a legal answer from sounding more certain than it is. That is how you make AI useful without making it slippery. This also changes how the economics should be shown on screen. The official number belongs in the primary evidence lane. 0.7% of a fleet-wide resource recovered. The scenario estimate belongs beside it, clearly labeled as a translation, not as a reported fact. If the assumed fleet size changes, the sidebar changes. If the assumed cost per compute unit changes, the sidebar changes. If the operational context changes, the sidebar changes. But the official claim underneath does not magically become stronger or weaker because the sidebar moved. That separation is the difference between analysis and laundering. A good system should make that separation visible, instead of hiding it in polished prose. For a legal team, that matters because clients often ask for the practical consequence, not just the doctrinal answer. They want to know exposure, likelihood, timeline, leverage, and business impact. Those answers are useful only when the chain is inspectable. Which authority supports the point? Which inference did the lawyer make? Which assumption did the client supply? Which estimate is merely a scenario? Which reviewer accepted it for this matter? The system should keep those labels attached all the way to the final work product. The future section of the AlphaEvolve paper is careful. It does not say discovery is solved. It says something narrower and more useful. Machine feedback can sustain test time compute scaling in settings where candidates can be evaluated automatically. That creates the possibility of distilling AlphaEvolve augmented performance back into future models, so the next generation starts with better priors. That is a possible improvement loop, but it is bounded by the environments where automatic evaluation exists, and it is not instantaneous. The paper says the current gains are moderate, and the feedback loops for improving the next version of AlphaEvolve are on the order of months. It cuts against the fantasy version of the story. The fantasy version says an AI system improves itself overnight until humans become irrelevant. The actual version is slower, more engineered, and more believable. Set up an environment. Define the representation. Write the evaluator. Run the search. Validate the result. Deploy the improvement. Distill what can be distilled. Then the next system starts from a better place. That is still powerful because it turns improvement into infrastructure. But infrastructure is not a magic loop. It has setup cost. It has evaluator cost. It has validation cost. It has deployment cost. It has feedback loops measured in engineering time, not just model tokens. But the ceiling is still the evaluator. The paper is explicit that AlphaEvolve focuses on domains where candidates can be automatically evaluated. Some domains in the natural sciences do not permit that cleanly. Some ideas require experiments. Some require high-level judgment before there is code to run. That is why the future is not everything becomes AlphaEvolve. The future is more domains will be converted into environments where search, evaluation, memory, and human judgment can cooperate. Even the newsletter-style future themes have to pass through that boundary. Hybrid systems may combine language-based hypothesis generation with executable evaluation. Learned evaluators may help judge properties that are hard to capture directly. Meta-evolution may improve the strategies used to search. AI-augmented evaluation may help humans formulate better test environments. Those are plausible directions. They are not official proof that all discovery becomes automatic. Every one of them still depends on the same question. Where does feedback come from, and can the system trust it enough to improve? The future, therefore, has two tracks. One track is expanding the number of environments where automatic evaluation exists. That means better simulators, better benchmarks, better executable representations, better ways to turn a messy problem into a checkable artifact. The other track is improving the handoff between human judgment and machine feedback. The human can propose a hypothesis, refine the formulation, reject a misleading evaluator, or add a missing constraint before the system spends compute searching the wrong world. Both tracks are slower than the fantasy. Both are more useful. They turn AI gets smarter into a concrete engineering question. What feedback loop got better? Legal work sits on the edge of that boundary. Law is not a scalar reward function. A brief is not correct because one score went up. A negotiation position is not valid because an evaluator approved it. But legal work has many reviewable artifacts. Sources can be checked, quotes can be verified, jurisdiction can be matched, red lines can be scoped, prior reviewer instructions can be preserved, draft branches can be compared, privilege constraints can be carried forward. That is the correct transfer, not legal AlphaEvolve, governed legal work. In Iris, the goal should be to make more of the matter reviewable, reusable, and stateful. The system does not replace legal judgment by pretending the evaluator is complete. It supports legal judgment by preserving the work that judgment depends on. That is the Iris operation for this arc, artifact-level transfer only. The transfer is not evolve legal arguments. The transfer is make legal artifacts reviewable enough that the next step can reuse them safely. A quote can be verified. A citation can be checked. A jurisdiction can be matched. A red line can be scoped. A reviewer instruction can be preserved. A privilege boundary can be carried forward. Those are the places where legal AI can become more cumulative without pretending law is a reward function. Iris should live on that boundary deliberately. Do not pretend the whole brief is machine gradable. Make the quote checkable. Make the source traceable. Make the red line scoped. Make the reviewer instruction persistent. Make the matter memory selective. Make the next task inherit the reviewed artifact. That is enough to change the workflow without overclaiming the law. That is the future worth building. The practical test is simple. Can the system turn a vague improvement hope into a representation it can actually edit? Can it build an evaluation path that measures the property people care about, or at least a faithful proxy for it? Can it keep enough history that yesterday's failed branch is not rediscovered tomorrow as if it were new? Those three questions decide whether the loop is real. If the representation is wrong, the system searches the wrong space. If the evaluator is wrong, the system optimizes the wrong target. If the memory is weak, the system spends money relearning what it already knew. That is why the AlphaEvolve story should not be flattened into AI invents things. The stronger version is more operational. AI systems can make progress when the world is converted into a governed search environment. Editable candidates, executable or reviewable feedback, remembered attempts, diversity preservation, model routing, and human validation at the boundary. That is the part that can transfer across fields, not the exact evolutionary algorithm, not the exact database, not the exact prompt format. The transferable idea is that intelligence becomes more useful when it is embedded in a loop that can accumulate state. For Iris, the long-run opportunity is to make legal work more cumulative at the artifact level. A checked citation should not disappear into a chat transcript. A reviewed red line should not become just another block of text. A rejected argument should not be regenerated without warning. A client-specific preference should not have to be re-explained every time the matter moves from research to drafting to comparison to revision. That is not automatic discovery. It is operational memory. And in law, operational memory is often the difference between a tool that feels impressive in a demo and a workspace that survives the day. Notice the constraint. The point is not to make legal work look like benchmark optimization. The point is to find the parts of legal work that can be made explicit enough to survive reuse. The citation, the quote, the jurisdiction, the redline scope, the reviewer instruction, the client assumption, the privilege boundary. That is where the system can compound without pretending judgment has been automated. So what should the viewer remember? Not the individual numbers first. The numbers matter, but they are not the general lesson. The general lesson is the system shape. Generate variation. Evaluate it. Remember what happened. Preserve diversity. Route work through the right model or tool. Keep scope and caveats attached. Let human judgment define the environment, inspect the result, and decide what transfers. That is the architecture behind the results. It is why AlphaEvolve is more interesting than another coding demo. It treats an LLM as one component in a larger search machine. The model proposes, the evaluator tests, the database remembers, the sampler selects, the system accumulates, and the human defines what kind of world the system is allowed to search. That last line is not a caveat after the fact. It is the control point. AlphaEvolve works because the human defines the problem, supplies the initial program, marks what can change, supplies context, and provides evaluation. The system is powerful because the loop is constrained enough for progress to accumulate. That frame also explains why so many legal AI tools feel impressive and then fall apart under real work. They generate, but they do not remember in the right form. They answer, but they do not preserve the evidence trail. They draft, but they do not know which text was in scope. They summarize, but they flatten caveats, reviewer notes, and rejected branches into a single smooth paragraph. That is not a matter workspace. It is a text interface. Iris has to be judged by a higher standard. Does the matter remember? Does the source stay attached? Does the caveat survive handoff? Does the red line know its boundary? Can a reviewer trace the answer backward? Can the next task start from inspected work instead of starting cold? Those are the questions that matter. Add one more. Can the system reduce rerun cost because it knows what was already checked? If the answer is no, then the platform may be useful as a drafting assistant, but it is not yet carrying matter work forward. The final test is a follow-up task. A new fact arrives. A partner changes posture. A client asks for a narrower red line. A new authority appears. A deadline moves. The system should not behave as if the matter just began. It should know which claims are approved, which sources are checked, which caveats are live, which branches were rejected, which red lines are in scope, and which reviewer instructions control the next step. The AlphaEvolve lesson is not that every domain needs evolution. It is that serious AI work is not one output, it is a governed loop. Mutate, test, remember, route, review, reuse. In science, that loop finds better programs, better heuristics, better constructions, and better infrastructure. In legal work, the loop has to produce something different. Source-backed, caveated, reviewer-aware matterwork product that can survive the next question. That last phrase is the final standard. Can it survive the next question? A one-shot answer does not have to survive much. It only has to sound coherent in the moment. A matter workspace has to survive continuity. It has to survive a new document. It has to survive a changed fact. It has to survive a partner asking why a sentence is in the draft. It has to survive a client asking whether the risk number came from law, business judgment, or rough scenario modeling. It has to survive another lawyer opening the file 3 weeks later and needing to know what was checked, what was assumed, what was rejected, and what still needs review. That is where most AI systems are weakest. They compress the past into conversation, but serious work needs the past as structured state. Not every token matters. Not every branch should be preserved. Not every draft deserves memory. The hard problem is deciding what becomes reusable matter state and what remains disposable exploration. That is why unlimited context by itself is not enough. The point is not to carry every word forward. The point is to carry the right artifacts forward with the right labels: source, scope, caveat, reviewer, assumption, branch, decision. That is the legal version of accumulation. The last screen should therefore not show a chatbot producing a perfect answer. That would miss the point. It should show a matter that has become easier to work on because the system knows what has already happened. One column for sources, one column for claims, one column for assumptions, one column for drafts, one column for reviewer decisions, one column for open questions. When the user asks the next question, the system should not merely append another response. It should route the request through that state. If the question asks for support, it should start from checked authorities. If the question asks for a red line, it should respect the track change scope. If the question asks for risk, it should show which assumptions are legal, which are business, and which are uncertain. If the question repeats a rejected path, it should say so. That is not decorative memory. That is operational memory. It lowers repeated token waste because the system does not have to rediscover the same ground. It improves handoff because the next lawyer can see the chain instead of trusting a summary. It localizes failure because a wrong answer can be traced to a bad source, a bad inference, a stale assumption, or an unsupported scenario estimate. Those are real user benefits, and they come from the architecture, not from a slogan. That is the standard every serious legal AI platform should be forced to meet. That is where Iris belongs in the story. Not as a slogan pasted on top of DeepMind, as the legal work version of the same deeper principle. The final Iris board should hold the entire chain: matter memory, verified citations, source-backed claims, live caveats, draft branches, track change scope, reviewer decisions, audit trace, institutional knowledge, rerun boundaries. That board is the answer to the one-shot failure from the opening. The future belongs to systems that can carry work forward, visibly and traceably. Not just systems that can answer once, however